Thank you for the introduction and thank you for having me today. Today I am going to talk about multimodal learning for videos. This work is done with many other colleagues in Google. So what is multimodal learning? Today, here by multimodal learning, I mean learning with more than one input data types. So there can be various data types available, like for instance, a tabular format of numerical data or categorical data in the form of tabular tables, or it can be natural form language, or videos, images, and also audios. So we have different types of data sets, data available, but then can we use multiple data types to build a model? That's what I mean here, multimodal learning. Then why do we actually need to use multiple modalities? We can take the human as a good biological model to benchmark. So as we know, humans perceive the world with multiple sensory systems. It's not just vision, but it also uses audition and touch, smell, and etc. And as you can see, they actually work together. When we look at how human behaves. So when there is a degeneracy in one modality, for instance, if let's say we don't we have a blind person, then although he doesn't perceive the visual input from his physical world, he can still learn spatial properties through different modalities like touch and echolocations. So, and also we know that sensory systems can educate each other. When we look at children learning, they spend hours gazing at their hands and touching and feeling objects. So they don't just learn things, they don't just perceive things through visual inputs, but at the same time, they actually look at how they interact and how they feel to reinforce their inputs to visual inputs, or better understand the visual inputs. And there is a study related to this. So basically, 8-month-old infants were those subjects were, they often struggle to retrieve objects from transparent boxes. So when they are asked to retrieve this object, this circular ball, which is wrapped, which is contained in a transparent box, when those infants played with those transparent objects before, they actually learned to retrieve it quicker. So it kind of represents how the physical touch and the other modalities help the infants to learn visual or spatial properties better. And also we know that when we make a conclusion, to make the conclusion more robust, we actually use multiple sensory systems together. So as an example, we can use this McGurk effect. I will show you 2 videos. This is the first video. You should look at the screen.
Ba, 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 ba.
So if you heard ba from this video, then you belong to the majority of people. So basically, majority of people actually hear this video as ba. If you
ba, ba, ba.
If you watch this second video clip,
ba, 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 ba.
There was a missynchronization, but if you heard fa, that's again you belong to majority. But as you can probably already know, those 2 videos actually the sound in those 2 video clips were actually the same, but the only video signals were different, but we still perceive the same sound differently. So basically, this clearly shows what we see actually affects what we hear. So this is like as a biological model, humans actually use multiple sensory systems to make a robust conclusion or like to better perceive the world. And if we look back and look away and then like see it in a different perspective, like machine learning perspective, the existing data are already multimodal inherently. Like the web, think about the web data. They are sometimes captions, like although they are in the same form of text, but like they are still they are different. Like they are captions or titles, descriptions, they have different roles. So those actually shows the multimodality. And also like if you think about the videos, then they are even like they are also by nature very multimodal. Like they contain sounds or human speech, human speech by the language, and also visual frames, and also they are associated with metadata. So they are very multimodal already. So it is kind of not very natural to use a specific modality in isolation. So like it's very natural thing to use multiple modalities together. And then how can we use them? So there are two different ways. So one is to use it for cross-modal supervision. So basically we use one or some modalities to help learn in other modalities. This exploits the redundancy of the information that are contained in different modalities. And another way to use is the fusion. So we combine the multiple modalities to make more robust conclusions. This exploits the complementarity between modalities. So like some information may be available only in particular, like in specific modalities. Then by combining that information, we can make a better conclusion. So basically, in this talk, I want to show you, like, introduce you some of our recent papers. Like, I will quickly go through like 4 recent papers. The first paper is like Look Before You Speak, visually contextualized utterances. This paper was published in CVPR 2021. So here, our goal is to build a visually contextualized conversational AI system. Basically, like humans, as I just said, like human interactions are facilitated through multiple modalities. It's not just language, but it also involves many other modalities. And what we focus here in this work is to use the visual modalities to better perform the conversation. But then the main challenge lies on the dataset collection, because like it's notoriously difficult to collect such a dataset, like performing conversations and then containing the the visual environment. So previous works mainly focused on like text-based approaches. It's still like hard to collect, but it was more maintainable. So that's why like they used Wizard of Oz technique to collect realistic conversation between humans. But then because of this special technique, like it was still not very easy to collect it in large scale. Another way, but there was also some research to do something related to vision. So what they did is they collected images and then asked people to talk about this, like ask questions specific to this image or video. And they also extended it to like make a dialogue. So they asked the subject to make a conversation about this particular, grounded conversation about this particular image or videos. So that's how they are collected, but they are very artificially created, because like it's not the visual environment that surrounds the conversers, but it was more like a random image or video that the speakers were forced to talk about. So here we wanted to think about more realistic scenarios, like where we actually deal with the environmental visual inputs when we actually model the conversations. But as I said, this is it's really hard to collect such a data set. So what we did in this work is to use freely available instructional videos that are from they are available from the online video platforms. So we can use those to learn from naturally co-occurring vision and dialogue. But this is not exactly the dialogue system itself, but dialogue modeling itself, because there can be some videos containing only one single speaker. So we believe that this can be used as a stepping stone towards the visually contextualized conversational AI system. So what we proposed here in this work is future turns prediction task. So future turns prediction aims to predict the next turns in a video clip given the previous multimodal context. Here, by the multimodal context, I mean the visual frames plus the user speech, like transcribed speech. So unlike the previous work that only focused on the text-based conversational AI system, we do have the visual inputs. And unlike the existing visual VQA or visual dialogue benchmarks, those visual frames are actually the environments that the speakers are speaking in. And we and also one thing to note is that we are not manually collecting the data set, but instead we are repurposing existing data set without manual annotations. So we can actually collect it in a larger scale. Because this was possible because we have those quite mature ASR systems available. And we formulated it as a multiple choice selection task. So yeah, we have 100 candidates, and then the task is to choose the correct next utterance. So, but we formulated it, although we aim to be, this work is, as I said, it's a proxy task towards the visually contextualized conversational AI system. But then, why are we not considering generation, and why are we considering ranking instead? The main reason is that this generation task is very hard to evaluate because the sentence generation itself has multimodal output distribution, so multiple correct paraphrases can be considered to be correct. Also, this future prediction itself also has inherent ambiguity. So given the same present, there can be multiple possible futures, valid futures at least, we can think of. And yeah, but so to deal with this, previous generation tasks collected multiple ground truth sentences, so that we can actually deal with the multimodality in the output distribution. But then this is, as I said, very hard to collect because we are currently using a single video frame, single video clip to collect this data set. Then it's almost impossible to collect multiple future, multiple ground truth futures from a single video, right? So that's why we wanted to check its model's capability of finding the next utterance, but generation metrics were not very reliable. Also, generation metrics are mainly based on the local matches, so it's difficult to capture the complex sentence structures or word semantics. So yeah, without collecting multiple ground truths, it's very hard to reliably evaluate the generated sentences. Also, yeah, so the last point is what I said. So basically, by formulating the task as a ranking problem, we can still use this recorder K, which is known to be better with multimodal output distribution, tasks with multimodal output distributions. This is our proposed model, but like we built a model fully transformer. I mean, our model is fully transformer based, and basically like we extracted multimodal features using sorry, like it's not fully transformer based one. So the first visual encoders are like CNN based, and we also use object detectors, and then like we use BERT for text encoding, and then we merge these, we fuse these information together to get multimodal embeddings, and then we also embed these future tense candidates, and then we use the contrastive loss to find the true positive. There are more details in the paper. I will skip this part because like my focus currently is like to introduce the task itself. Like the focus is to show that like we introduce this kind of task to validate the model's capability of visual understanding, and also like this is by showing that multimodal models actually performs better than text-only model, like we kind of validate our argument that like visual modality is important for modeling conversations, human conversations. We built different data sets, like as I said, like we proposed the future tense prediction future tense prediction task, and the data set that we built is how to FOP. And this data set is built from how to 100 million data sets, so it's at a large scale. It contains 35 million training examples and 120K validation and test examples. And we also built CoinFOB. There is a data set called Coin. We repurposed this data set too, but because this is a data set with manual annotation, the scale is quite relatively small, actually quite a lot smaller than the previous one. And here we can see how the scale matters. And so for each data set we collected one true next occurrence, which is available from the video, and 99. We also collected 99 randomly sampled next occurrences from the split, so that like we selected the negatives randomly. And additionally, because we are predicting the next occurrence, in the next occurrence prediction, like the sentence structure is quite important to predict the next occurrence. But can we actually test the model's capability of predicting what's going to happen next? Like not in the sentence structure sensitive way, so that like we wanted to test that capability by formulating this next step prediction, because Coin is annotated with the steps of the instructions. So we tested, so given the current speech ASR and the visual frames, the task is to predict the next step in the instruction. And there are some video question answering data sets that we use. I will introduce those at the end. So yeah, when we see the results from how to FOP data set, what you can see is that like multimodal models, like which are those, like all those multimodal models actually outperform compared to the text only or visual only baseline models. And yeah, and like what we also see, these are the qualitative examples that we found. So this red one is the prediction of the text-only model, and the green one is our multimodal models prediction, and the checkbox represents the ground truth candidate. And as you can see here, like and the boldface words here, they represent the clue that shows this candidate is actually the ground truth. So by checking the watermelon, we can actually know that this is the ground truth utterance. But this watermelon is not available in text input. So here in the transcript, there is no clue related to the watermelon, but as you can clearly see, the visual frames actually contain the watermelon. So the model, our multimodal model, could actually capture this information from the visual inputs and then like could correctly predict the ground truth next occurrence. And when we tested in on coin FOB dataset, we could see that like the multimodal models sometimes like they underperform compared to the baseline models, text-only baseline models. This, however, this happened when when our dataset was very small. So when we use small datasets, the results sometimes can mislead us. So like we might conclude in different conclusions. But then like when we use the how to for pre-trained model and then fine-tuned on this task, like we could obtain like 71% of recall at one. So it's quite high performance. And compared to the like text-only baseline model, like it was pretty much reliable. I mean, pretty much like double of the baseline score. And when we tested on like next step prediction, it was what was interesting is that like compared to like previously the text-only model actually performed much better than the vision-only model. However, in this task, like vision-only model actually performed better in mostly better than the text-only baseline model. So depending on the task, like which modality is more important is decided. So predicting what's going to happen next in the form of the class, actually visual information contained a lot more information. But if we are predicting the text form, natural language text format, then the text structure and the context might be dependent on what's said before. So that's why like text model was important. But in both cases, multimodal baseline and multimodal models actually performed much better. And what we found also in this work is that, like as I said, we didn't actually manually, we didn't perform any manual annotations. So basically, our data set is from unannotated data set, and we trained models using using that data set without any additional cost. And then when we transfer this model to other tasks, we actually could outperform existing state-of-the-art models. So in this table, as you can see, like even with Scratch model, like ours was performing like comparatively comparably to like existing state-of-the-art. But then when we use this pre-trained model on FOB benchmarks, I mean how to FOB data set, we could actually outperform these models, like existing models. And here, like Hero is also pre-training method. So state-of-the-art pre-training method at the time. And we could find that like our model actually was also performing better compared to existing pre-training benchmarks. So this task, FUP, is quite a reliable pre-training task too. That's what we found. So this is the first work. If you have any questions, I think I can talk about I can answer. If you don't, I can move quickly because I think I should speed up a bit. So the next paper is end-to-end generative pre-training for multimodal video captioning. And this work is recently presented in CVPR this year. So the target downstream task in this work is multimodal video captioning. Multimodal video captioning requires dealing with two different texts. One is the input text, where because like we are generating caption from multimodal video, where which consists of like visual frames and the ASR. So this ASR is one source of the text, and the other source of the text is the target text that we need to generate, the target caption. However, it is not very straightforward to train such a model with unlabeled videos. Like, unlike like other tasks where the pre-training actually helps a lot. For this task, it's kind of hard to come up with a good, reliable pre-training task because when we use ASR as a training signal, but here we need two different text sources. But here, but with unenabled videos, we only have a single text source. So that's the main challenge. So what previous approaches had done is that like they used they masked out some part and then asked the model to generate this masked part or like reconstruct the original sentence. So that's how they split it one single sentence or one single text into two. However, they only like these approaches provide only partial supervisions for the input and output text, and so and also like they mainly use the pre-extracted visual features to avoid heavy computations because they used 3D CNN-based approaches. In our proposed method, we leverage these future utterances as an additional source of text signals. So the model is asked to generate the next utterance given the current visual frame and the current text. But our downstream task is caption generation, but not future prediction. And the future utterances are known to be less grounded to the input visual frames. So what we also propose is to use bidirectional generation. In addition to the previous future utterance generation task, which we call forward generation, we also introduced backward generation. So in backward generation, the current visual frames and the next utterance are fed as the input, and then we predict the model predicts the current ASR. So in this way, the generated target text is more grounded to the visual contents. So forward generation actually enforces, this is our overall framework. We have forward generation and backward generation. And as I said, forward generation takes the present utterance and then generates the future utterance. While in the backward generation, like we put future utterance as the input and generate the present utterance. In this way, like forward generation actually enforces the multimodal encoder to properly fuse the multimodal inputs, like grounded inputs, and in the backward generation, sentence decoder is enforced to generate the more grounded sentence to the visual input frames. And what we found here is that like one very important takeaway note is that joint pre-training of encoder-decoder is very critical for multimodal video captioning. And as you can see, like we compared to like some pre-training baseline models. So compared to no pre-training, just pre-training encoder already helps a bit. But compared to those methods that pre-train both encoder and decoder jointly, like it's much smaller. The gain is much smaller. And among those techniques that pre-trains both encoder and decoder, our method was the best. And what we also found is that like for our full model, we actually use the publicly available weights like BERT and GPT and Vivid weights. But we also tested just to train from scratch using only our pre-training method only. And then like we could see that our model was still perform much better than the existing SOTA, and like the gap was almost like not that big like compared to our full model. So our pre-training technique itself is quite a strong pre-training technique, even from scratch. And so applying this to 4 different benchmarks, we actually achieved state-of-the-art in all 4 benchmarks. And one important thing is that like some of them, like MSR VTT and ActivityNet captions, they are quite different from the pre-training data set. like the domains are quite different, but like still we could achieve quite good performances on those data sets too. And these are the qualitative results. The left one, as you can see, like here, the ASR actually made a mistake. So instead of predicting source, it recognized the speech as source. But by using visual information, the model was actually able to correct this. So it not only corrected the source into source, but it actually precisely predicted the name of the source, like sriracha here in this case. And the next one, as you can see, like the first part of a man in a suit can be only inferred from the visual inputs, while talking about mental health can be only inferred from the like text input. So like the model was actually trained to properly use the multiple modalities in this case. And we also tested our pre-trained models. Although like our model is designed, our framework is designed to tackle the multimodal video captioning, we transferred our pre-trained model to non-generative tasks. And there we could actually see a lot of gain compared to its comparable models. And then like in video QA, like we could achieve like the state of the art. And this is the second part. And do you have any question? If not, the next paper that I will present is called Avatar, Unconstrained Audiovisual Speech Recognition. In this work is going to be like presented in Interspeech this year in September in Songdo, Korea. So yeah, if you are interested, you can come and visit our poster too. So here in this paper, our goal is to build a robust speech recognition system. And to do that, we want to incorporate the visual context so that visual context, because we believe that visual context can help with speech recognition, especially when the audio is noisy or corrupted. So the task is, we are not only taking the audio stream, but also visual frames. And our output is the transcribed text. Previous studies mainly focused on previous AV-ASR studies mainly focused on using limb motions to correct the errors of the transcriptions. But there are cases where limb motions are not available, like speaker can be far away, or the video frames can be blurry, or like egocentric viewpoints, like videos with egocentric viewpoints do not contain the speakers. And nowadays, like because of the COVID, like there might be some videos with facial masks. In that cases, like we cannot use those information. Although it's very obvious cue, there are cases we cannot use them, but there are other objects available too in the visual frames, so we can probably use those information to correct the erroneous transcriptions. And also the previous studies actually used automatic tools to build benchmarks. So they used the user-uploaded captions and force aligned it to the speech, and then filtered those top scoring samples. But because they only sampled those top scoring samples, they are inherently very clean audio, because having high force alignment score already means that it's quite clean to align the text to the audio. So they are very clean, which means these samples are very audio dominant. So without visual information, most of the examples can be correctly transcribed. And the ground truth transcriptions are also noisy because they just use the user-uploaded captions. As you can imagine, user-uploaded captions may contain some erroneous errors. Like, as an example, you can think like some speaker names sometimes come before what they said, the captions. So in the YouTube videos, you can imagine. So, and also there are training data sets are quite tiny. So we actually use pre-training techniques to deal with this tiny training data set. So at the model side, we proposed end-to-end trainable transformer with early modality fusions. Previous works mainly used the pre-extracted visual frames, visual features, so that they could not fuse this information at the early stage of the encoder. But instead, in our case, because we used the fully transformer-based architecture and we adapted this MBT architecture, we could fuse the information at an earlier stage, and then we could train the entire network end to end. And at the training side, what we propose here is that we propose a novel training strategy based on word masking. So we instead of randomly masking out some of the audio signals, we first align the text with the audio signal and then masked out specific words so that we can actually distract the model from inferring the entire word from the audio. So that in that way, it's encouraging the model to look at the visual information to infer what is said, what is actually said. We tested our models in 2 different noise settings. So first one, like in artificial noise settings, like we introduced like random artificial noise. 2 different types of artificial noise. First one is burst packet loss, which mimics the transmission errors, transmission noise. So we randomly masked a chunk of the audio signal in this case. And the other one is environmental noise. We added audio signals from like noise category, like those audio signals belonging to noise category in audio set data set. And what we observed is that like vision helps in any case, but using masking strategies during training actually improves performances a lot. And we achieved the state-of-the-art performance with and without noise in this particular benchmark, which is called how-to. And we also evaluated our model on real noise setting. However, there are not reliable evaluation benchmarks, so we built a new test bed called VSpeech. To build this VSpeech data set, what we did is we first collected the videos that contain both user-uploaded captions and ASR, and then we made an alignment between these 2 texts, and then selected the segments that are hard by sampling those samples that have very low word error rates. High word error rates. So we have those hard samples. Then what we also did is we measured visual and text similarity, and then we sampled those examples that have high similarity scores, so that there are high relevance between like visual signals and what is actually said. And then we did manual transcription so that like, we can actually have clean ground truth data set. And in the real world noise setting, like what we could find is that our data set, this new data set, is effective even without the artificial noise. Although like previous data set, without artificial noise, it was kind of hard to show the benefits from visual input. And also, similarly to the previous results, like we could see vision helps in all cases, and also masking strategies improves the performances. These are some qualitative examples. Like this video is quite contains strong background noise, and the audio-only model actually fails to correctly recognize chain, and it instead outputs chin. But our audio-visual model correctly recognizes it as chain. You can hear.
To sharpen your chin, that's for sure.
And the second example here, the speaker uses non-American accent. Quite a strong non-American accent, and here is this is the error that audio-only model makes.
And repeat the sample for the opposite side.
And here, like the speaker uses quite ambiguous pronunciation, so the model fails. But our model, audiovisual model,
thumb reaches for the coin.
Yeah. Yeah. So even in when we like, so basically, like I showed in the first work, I showed like we can build we can repurpose existing data sets to test the visual inputs. I mean the model's capability of understanding visual modalities towards the visually contextualized conversational AI system. And then we also showed that for the text generation, like visual modality actually helps, and also we can use pre-training to improve it. And even here, like we are, I mean, visual information actually is effective improving in improving like audio, like speech recognition task. And finally, like what I want to explore is the dataset side. So the title of the paper is Video CC, Learning Audio Video Modalities from Image Captions. And this is recently announced to be accepted for like ECCV 2022. So it will be presented soon in Tel Aviv. And yeah, so why is the paired video and text data set so valuable? Like, you know, like I would like point out this point, like natural language is used for communication, while videos are used for perception. So you perceive the world through visual modality, and then like you express and communicate it through natural language. So there should be some connection connecting those two different modalities, and that's what this video and text data sets are doing. So this is quite important data set. However, it is quite also difficult to collect such a data set in large scale. So if it's large scale, then they are noisy. So because they are collected automatically. On the other hand, like those manually annotated reliable benchmarks are quite small. So this is the problem that we have in most video tasks. However, in contrast, like in image domain, there is quite a large data set called conceptual captions data set. So the situation there is quite relatively better. So in this work, we wanted to leverage this image data set to build a large-scale video text data set. So what we did here is that like we use this image from the image captioning data set as a seed image, and then we sampled like frames from videos, and then computed the similarity score to select matches. And then if some frames are selected as the matches, then we extract the video clip surrounding that video frame, and then transfer this image caption to those videos. This is how we generated a large-scale video captioning data set. So we, for the dataset collection, we performed some evaluations. So threshold tau is to determine, threshold tau is the threshold that we used for determining the matches. And so as you can see, when we, as we increase the threshold tau, the number of samples decreases quickly. And as we increase the threshold tau, the zero-shot retrieval performance also decreases because the number of samples reduces quickly. So what we found is that 0.6 is quite a reliable threshold, so we used 0.6. And this second table is showing the length of the clips that we extract. So as you can see, as we increase the length of the clip, it actually kind of converges. The performance kind of converges. So like we chose the length of the clip to be 10 seconds long. And here what I want to show is that like our data set is relatively more diverse and balanced compared to how to 100 million dataset. How to 100 million dataset is it only contains instructional videos, whereas our dataset actually covers all the videos in the YouTube. And also the dataset, as you can see, like the domain of the data, I mean samples, are quite well balanced in the pie, as you can see in the pie chart. So those are some examples that we collected from VideoCC dataset. The left images show the seed images, and then right side they are the frames that we they are match frames. These are more examples. And we also tested, like, performed some preliminary test to see the quality of the data set. We manually asked the raters to rate the samples, and then in 3 different scales, and then 91 samples are annotated with to be relevant. And when we use this data set for video retrieval, we could achieve, I mean, compared to how to 100 million data set, which is 20 times larger, like in these experiments, we could actually perform similarly or slightly outperformed. And in zero-shot settings, it was actually much better performing. Like, these are the zero-shot performances compared to how to 100 million. Our data set is actually much more effective. And then we also performed zero-shot video captioning, and our new data set actually improved the performances a lot compared to how to 100 million data set. And we also, because we are transferring the image captions to video, videos also contains sound. So basically, we are transferring the captions to audio or sound too. So we also performed audio retrieval, like as the downstream task. And then we found that our data set actually improves a lot in both zero-shot setting and fully trained setting. So this is the last paper that I wanted to present. So yeah, I wanted to say that multimodal, it's, as I said in the introduction, it's quite natural to use multiple modalities together. So, and we actually could see that using multiple modalities, we can improve the performances of existing models. And then there are still very many challenges unexplored, like data set, how to improve even further, for the data set. For the languages, it's quite easy to collect large-scale data set for language modeling, but how to build that large-scale data sets in videos, that's quite questionable yet. So yeah, there are many questions. So yeah, I want to invite you to this research area. Thank you for listening.